Hello students, today I am here to discuss about the John Teller effect. You know the coordination compound, what are coordination compound and its properties, its nomenclature. These are the basic ideas of the coordination compounds, and the next advanced portion of coordination compound is the CFT, that is a crystal field theory. There are many theories come forward to explain the metal bonding in a case of metal ligand bonding in a case of the coordination compound. So those are MOT, that is molecular orbital theory, CFT crystal field theory, and valence bond theory. So valence bond theory had its own drawbacks, and later CFT came, and it's been somewhat or a major of the success than the VBT in explaining the metal ligand bonding in case of the coordination compound. So according to CFT, there is a phenomenon, a peculiar phenomenon by the name CFS, that is crystal field splitting, takes place during hybridization. Before the hybridization, that is hybridization is a common phenomenon which occurs before the bonding. So in a case of the coordination compound, before hybridization, a process called as CFS, that is crystal field splitting, takes place, and after that hybridization, and thereafterwards the bonding takes place in a case of the coordination compound. So CFS, then with the CFS there is one more phenomenon that takes place as the John Teller effect. The phenomenon that is invented by, or that is observed for the first time by John and Teller. So the name is John Teller effect. Now what is John Teller effect? That is, any nonlinear molecular system in its orbitally degenerate electronic state would be unstable, and that would get stabilized by undergoing distortion in its geometry, and thus by causing a split in its orbitally degenerate electronic state is the statement, and the phenomenon is known as John Teller phenomenon, and statement is known as John Teller effect. Now, the distortion in the geometry of the nonlinear molecular system thus produced is known as John Teller distortion. Now, in its orbitally degenerate electronic state means electronic state which can be represented more than one form. One electronic arrangement is called as orbitally degenerate electronic state. So any nonlinear molecular system, if it is unstable, then it would get stabilized by undergoing a distortion, that is a John Teller distortion. So by the distortion it attains the stability. So in order to illustrate this particular John Teller effect, we shall take an example of the copper complex, that is Cu2 plus copper complex in an octahedral complex where it is surrounded by the unidentate ligands. So let us study the John Teller effect by taking the octahedral complex of copper where the copper is surrounded by the unidentate ligand. So the CFS takes place in all electronic rearrangement. There is no particular electronic rearrangement for the CFS to take place, but in order to observe the John Teller effect, there is a particular ground state electronic configuration. We can't observe the John Teller effect in all other electronic configuration. There is a particular configuration on in which we can observe the John Teller effect. So in a case of the copper, that is in its C2 plus ion, ground state electronic configuration, if it is T2G6Eg3, you know T2G, Eg, T2G consisting of three set of orbital, that is dxy, yz, xz, whereas Eg it is consisting of two set of orbital dx square minus y square, dz square. As we are considering the octahedral complex, you know how the crystal field splitting takes place. That is, T2G will be in the ground state and Eg will be in the higher energy state. If the ground state electronic configuration is T2G6Eg3 means we have to remember T2G in a down portion, so it is completely filled. there is no problem with the T2G because it consisting of 3 orbital, T2G 6 electron. That means the ground state is completely, or lower energy state is completely filled, and there is no chances of representing it in a different way. But there is a problem with EG, as it consisting of 2 orbital, dx square minus y square and dz square. As there are 3 electrons, there can be 2 possibility. One possibility is T2G6 dx square minus y square 2 dz square 1, and the next possibility is T2G6 dz square 1 and dx square minus y square 2. Now what happens in a possibility 1? So in a possibility 1, as there are two electrons in a z orbital, and there is only one electron in the dx square minus y square orbital. Now the electron density is more in the z orbital, that is dz square orbital is having a higher electron density than dx square minus dy square. Now what happens when condition applies like this? You know, according to CFT, the metal ligand bonding or interaction between metal and a ligand is purely because of it is purely in terms of the electrostatic interaction. That means there is an attraction between, how the attraction between positive and negative poles takes place. Same thing will occur between metal and a ligand. Now in a possibility 1, dx square minus y square is having 2 electron and dz square is having 1 electron. Now dx square minus and y square has the more electron density. Now what happens, as the maximum number of electron is placed in dx square minus y square orbital, now there is a screening effect of the positive charge on the metal ion and the negative charge on the ligand takes place. The electrons present in the middle, now it screens the positive interaction between positive charge of metal ion and the negative charge of the ligand. Now what happens, there is an less attraction between electrons present in dx square minus y square orbital with the electrons of the metal ion. Due to this, there is a less attraction between the metal ion and the orbital dx square minus y square. Because of this, a bond is elongated along dx square minus y square orbital. As a single electron is present in dz square orbital, the screening effect is less, or you can say there is no screening effect between the z orbital and the metal ion, because a single electron is present in a z orbital. So because of that, ligand and the metal interacts more, so there is a more attraction. So as there is more attraction, bond between metal and ligand is contracted, it gets compressed along z direction, where it is elongated along x and y. Now because of these type of developments, octahedral complex geometry been compressed to tetragonal, and this causes the distortion of the geometry where it attains the stability. So John-Taylor effect, mainly it is observed in those cases in a nonlinear system where it is most unstable. So by undergoing distortion, it get distorted and the geometry there is an gaining of stability takes place. And if we consider the possibility number 2, that is dx square minus y square is having 2 electron and dz square is having 1 electron. Now exactly the reverse of the first case takes place. Now electron density is more along dx square minus y square orbital, and now what happens, the screening effect takes place here now, and the interaction between the ligand and metal in that particular orbitals becomes less. So now again there is an repulsion, more than an attraction, there is an repulsion takes place. So because of that the bond is get elongated in the x square minus y square orbital, and in a case of dz square bond is get compressed. So now again the geometry is lost. So again in any nonlinear system automatically the geometry being lowered to from its higher to lower geometry, and there is no extra energy is required for those phenomenon. That is the the energy of the degenerate orbital and energy of the split orbitals, it takes place automatically. There is no change in the energy of those orbitals. So when I said the possibility, that is T2G6, it is possibility number 2, that is dx square minus y square is having 2 electron and dz square is having 1 electron. Now as I told earlier, dz square is having a single electron, the bond is elongated along dx square minus y square. The bond is elongated along the direction x and y, or why? Because I already told dx square minus y square is having more electron, it screens the metal ion from bonding with the ligand. So it is elongated in that direction and it is compressed in the z direction. In the first case dz, it is the z square is having 2 electron and the x square minus and y square is having 1 electron. In that case the bond is compressed along x and y and this is elongated along z direction. So this is all about the John-Teller effect, and same type you can observe in a case of square planar complexes, but here that is it's because of the arrangement of the electron, but there we study the, in a case of square planar complexes, what we study the CFS, that is crystal field splitting, that we study in a square planar complexes. There also we are removing the ligand along the z direction. So because of that the z orbital is having a very low energy. But here it is not removing, but here it is because of the arrangement of the electronic arrangement of the electrons, arrangements of the electron, difference in the arrangement of the electron. And one thing we have to remember is John-Teller effect can be observed only in such electronic rearrangement where the arrangements can be in a one or more manner, like we had as we have taken T2G6 Eg3. So Eg3 can be accompanied by 2 electronic arrangement, that is dz square 1, dx square minus y square 2, and another possibility is dx square minus y square 2 and dz square 1. So this is all about the John-Teller effect. Thank you.